Thanks, Ahmed. So in our efforts to pursue geospatial science and technology research at Oak Ridge National Laboratory, we are supporting national security, energy, and environmental missions. For some great examples, we are characterizing the built environment as well as human dynamics using machine learning, high performance computing resources, as well as EO data. So I thought today, in line with the goals of the workshop, I would highlight three key challenges that are motivating most of the projects that I've been working on for the past 4 years at ORNL. The first being how to enable machine learning methods to learn from limited amount of labeled ground truth data. The importance of that is, as we know how expensive it is to collect data, we're trying to bridge the gap between the loosely or easily available data and then take advantage of the few expensive data that can be collected. The second challenge would be how to develop machine learning techniques that can allow us to address challenges that arise as a result of spatial temporal adaptation. This tends to be the biggest motivator of most of my projects. And I'll talk briefly about a couple of techniques that we are pushing behind to enable the scaling of some of the products that we're generating from satellite imagery. The last challenge has to do with seeking machine learning workflows. We do have access to the supercomputing resources. However, the deployment of machine learning within supercomputing resources requires a bit of work in terms of maximizing and enabling the resources to be able to compute and have training and acceleration of inference that can give us models in times that we expect. So as we see from the picture on the right, I mentioned the spatial temporal adaptation. A lot of our imagery is collected at different times in different spaces. So the idea of having to develop methods that can then be applied across the entire country does require that we take time to address these differences. So to start with the learning from limited labels, we'll just go through an example where we focused our efforts toward creating a weakly supervised learning algorithm. And the task here was to come up with a framework that would allow us to count the number of grave sites by making use of the satellite imagery. So this is a task that can easily be achieved by bringing in object segmentation models. However, with the object segmentation models, the assumption there is that you do have access to a lot of ground truth information, which would mean that would need people to actually go to the imagery and draw polygons on each of the grave sites to generate the training labels. As expensive as it is, we started to think in terms of, okay, what if we just impose this as a question where we have a bounding box where we can easily have people just give us a rough count of how many grave sites do they see within an imagery. Could we then develop models that can then be used to perform this regression task? It turns out that that by itself is also not enough because the counts that you get are not as good as what you would get if you had a fully supervised framework that is taking advantage of the pixel labeled data sets. So the big question in this project is, can we bridge the two, take a little bit of what's coming from the object segmentation labeled data, and then the easily available data set to combine this into coming up with a single regression framework. So with the recent advances in deep learning, it turns out that the architectures are flexible enough that you can only, for example, from the object segmentation models, you can make use of 1% to 2% of the data and then have most of your data that is coming from the object counts, give you a model that can be used to estimate the counts. So looking at this test image here for some results, turns out that, in terms of comparing what the model gives you and what the human does, we fairly, achieving numbers that are very comparable, and it's a useful way for us to then scale this work and automate it where we don't have people go and start counting the objects by themselves. Moving on to the second challenge, now going back to the spatial temporal adaptation, My early work started by creating workflows where the idea here, again, was to acknowledge that whenever you have some acquisition conditions in place and you have two domains, we often train in an area or on a collection of imagery where we can easily gather training data. However, the main interest is in deploying these models where you don't have those accesses. However, in between the way, if the acquisition conditions are different from what you have in your training data, that throws off your models. So we spent a lot of effort coming up with transfer learning techniques and active learning methods that enabled us to then have these human in the loop workflows to then keep on adding data so as to improve the methods to scale and generalize to new testing areas. Most recently, I would say about 8 to 9 months ago, we started taking a different view at how to enable the spatial temporal adaptation. So what we're doing in this approach is to take a view of rather letting the data structure drive how we actually generate the training sample, the collection of training samples. In this approach, we build manifolds in a way that we partition our data set into different buckets. And then from these buckets, we create our models so that when you start to train the models, you enable that division that is in your partition space to inform some level of homogeneity, so that homogeneity is beneficial when you estimate your models. We need not now start to look at complex models, because if you have homogeneity in your buckets, that informs an easier model that you can estimate. The other benefit that's coming out of this type of workflow is that during inference, we can take advantage of all the models that you train at once and deploy inference all at once, and allowing us to do a wider reach across different geographies all at once. And this can be seen in this example here, where we can see that by looking at the building mapping project, we're able to sort of like just make use of 4 different models that are coming from the 4 different buckets. However, if you look now at the geographic extent of the imagery, we mapping across North America and in Africa by just reusing the same models. And I should mention that this kind of framework is agnostic to the application that you're looking at. Once you've done the partitioning, you can create different labels on top of the partitioning and then take advantage of that fabric underneath to create models that can be used at global scale. The last project on this spatial temporal adaptation is a more recent approach that takes the view that a lot of the acquisition conditions that we see in our imagery, they are due to, as I showed on the acquisition conditions. So the question that we ask is, can we create frameworks that can learn from the images to separate, the low level, signals that are caused by those conditions, and then extract the signal that is invariant to the noise that is present in the image. So it's an approach that's taking advantage of development that came out of the NeurIPS community in terms of disentangling the representation. So what we think would come out as a beneficial to this kind of approach is when you fuse, say, in your source domain where you have access to the labels, you can then start to train things in a supervised and unsupervised manner. Unsupervised in the sense that you do have access to a lot of unlabeled data in your target space. So if you co-train the two, this should then start to inform us to move towards models that are robust and that can also generalize across larger applications and larger spaces. The last point, key challenge, has to do with how we are enabling workflows within the HPC environment. The idea being that we are training models that are very complex. So we need workflows that can allow us to accelerate the training. And as well as during deployment, we need frameworks and advanced workflows that can allow us to accelerate how we deploy our models. Inference is a big part of what we do, because we are generating image products for country scale. So having to spend some time thinking about this problem is starting to be very beneficial for us whenever we have a large volume of imagery that we need to deliver. To wrap up, I highlighted 3 key challenges that I hope that during the course of these next 3 days, we can touch upon, expand on these, and I see these as relating to some of the earlier arguments that were presented by some speakers. Thank you.
Hello, everybody. So Dalton kind of teed me up nicely with his last bullet here. So today I was going to talk about this concept of teamwork in from the perspective of software and hardware, though, because I think sometimes that gets a bit decoupled and overlooked, and particularly NVIDIA's perspective. Okay, so a lot of folks, if you've heard of us before, most of the people that I run into think we're just like the gaming company. We build hardware that makes video games go faster, and that is certainly true. And it's a big chunk of our business. If you've tried to do any of these techniques that Dalton just talked about, you probably quickly realize things go really slow on CPUs, and that's how you potentially have found a GPU also, references to those in the literature. And so AI has become a really big industry for us in various sub-industries. I primarily focus on sort of geospatial applications in the federal space, hence my background and what I do at NVIDIA. But there's a lot more that we're doing at NVIDIA besides the hardware aspect of it, just building cool chips. And so that's sort of what I wanted to highlight, because as you all are evolving and how you're using machine learning and deep learning techniques, some of this stuff I think goes unnoticed. Okay, so this is a giant chart of some stuff that we build, and mostly people think about the stuff on the bottom. So those are just the chips in various form factors, data centers, cards you stuff into workstations, whatever. But on top of that, we actually have this very rich software stack that has gone far beyond just CUDA. If you've heard of CUDA, it's our programming model that we expose to the developer. That's how you actually make stuff go on the GPU. But as it's evolved, we're on CUDA, I guess 10, almost 11 now. We've started to build much richer focused SDKs and have started to integrate those tighter into different applications. So you're starting to see these bundles of CUDA-esque SDKs that are focusing on machine learning, deep learning, more traditional HPC, and then there's this whole side that does virtualization, which I'm going to largely gloss over. With deep learning, we have super tight integration with all frameworks. The frameworks being, TensorFlow, PyTorch, MXNet. These are the languages that machine learning engineers or data scientists write their algorithms in. We work hand in hand with Facebook and Google and Amazon, the folks that maintain these frameworks, to provide them acceleration, the code to actually get their stuff to go faster. But I wanted to highlight that we're building this hardware and this software together. That is really the only way we're able to achieve the speeds, is to think about the architecture holistically from these two perspectives. And so I just wanted to highlight a couple of these things, and then point out that all the software is free. If you're using a GPU, you guys could just go grab this stuff and start using it. So one thing that's kind of an interesting hybrid approach was the introduction of tensor cores. These are actually circuit design components on our chips that are purpose-built to do mixed multiplication accumulation functions. So think about in backpropagation. In a deep learning algorithm, you have to do these large matrix multiplications and then accumulate down to get to your weights. That happens repeatedly over billions of parameters. And so if you can control the precision, actually the bit precision by which you execute those computations, you can get some speed up without sacrificing accuracy. And so tensor cores is an example of hardware that we purpose built for deep learning training, and then expose in software, mainly through these automatic mixed precision libraries in TensorFlow, PyTorch, all of these things that tend to be 2 to 3 lines of code that you add to the top of your training script, let's say, and you sort of automatically get the benefit. And we have various diagnostic tools to tell you if you're actually lighting up the tensor cores to get those sort of speed ups. But when you start to think about the problem this way, when you're trying to get science at speed, these things matter at the scales of data you guys are talking about, and these big multiplicative increases in performance become impactful. And so here's some reference for training and inference for some traditional algorithms, which are not noted on here. Oh no, yeah, it is. It's ResNet 50. And comparing them versus different sort of architecture setups. And these are all running on the Volta chip. Another way you can tackle this on the inference side, which Dalton was also just talking about, is how do you actually deploy a trained model in production? You spent a lot of time building lovely training data, errors or not, and now you're satisfied with its accuracy and you'd like to push it out into the world. A lot of times the compute footprint required for training isn't necessary for inference. You're not doing backprop anywhere. We're just doing a straight shot through the network forward prop. So TensorRT, you could think of as a compilation engine for models trained on our GPUs. It takes in model architectures from all of the major frameworks, along with calibration data. A big part of production is you want to preserve your accuracy when you push a model out. And so TensorRT is a whole system where you feed, it's an API, there's Python bindings and C++ bindings. It actually ships inside of TensorFlow. So if you're using TensorFlow 1.7 or above, you have this and you might not even know it yet. But essentially you feed the algorithm or the model architecture, so your architecture file, along with your weights and calibration data, and it looks through the orders of operations you're asking the GPU to do, which layers make the most sense to compile down to a single CUDA kernel, for example, that would happen in a single clock cycle. What can be merged vertically and horizontally across the architecture to become more efficient. And what it produces is sort of a runtime version of your model that you can then deploy to any of our GPUs that might be out in the world getting ready to run these things. And you can target particular algorithms because certain cards have certain capabilities with regard to bit precision. And so we bundle all of this up and provide this in container form. There's an inference server that's free to go grab in a container that allow you to deploy these models. It just sits an endpoint in front of the thing you'd like to ask a question of, and you send your data to it. There's a lot of engineering that's already been done that you guys can just benefit from if you're using GPUs. And what you can get from doing something like this, again, big speed ups. If you can reduce the compute footprint and you have a very inference heavy load, you can shrink your compute requirements, which yields shrunk power consumption, less heat consumption, or heat production, I should say, all the sort of benefits of shrinking your compute footprint. Another sort of software approach we've taken is containers. Hopefully most folks are familiar with Docker, the Docker engine container. You could think of it as like a lightweight VM. You take your application and all of the bits you would need fundamentally to run that application, and you kind of shrink wrap it in a container. And so Docker engine has opened up a lot of opportunities in collaboration and portability with regards to models, algorithms, reproducibility in scientific work, things like that. And so we sort of jumped in on this and produced some work that I think now has largely been shifted over to the Docker project itself to enable GPU-enabled containers. So if you have a workload wrapped inside a container that needs access to GPU compute, the NVIDIA Docker runtime configuration is what manages that interaction between your application and your host system. But along with that, we started cranking out our own containers as well. So you can go to ngc.nvidia.com, and I'm happy, I'll obviously be here for the next 2 days, so to point people to where this is explicitly. But we publish monthly containers. The number of containers is growing all of the time. These have model training scripts. We stamp out a container for PyTorch, for TensorFlow, for MXNet every month that includes all of the optimizations you would need for our hardware. A lot of times the branch of PyTorch or TensorFlow is ahead of what's in the public repo because we push PRs to those repos and then they have to integrate them into the baseline. So as we add improvements to CUDA and chips or find issues that haven't necessarily bubbled up to the framework level API, we actually have developers at NVIDIA that write that code and push it to both the Google team, like Google's TensorFlow developers and Facebook's PyTorch developers, things like that. We also publish models and workflows. The last thing I wanted to highlight, if you're not doing deep learning, there's like all this other stuff that's not deep learning, but that can also go faster too. And so a project I wanted to just mention, and I won't have time to go into, is the Rapids project. This is an open source effort by NVIDIA. It's sort of a consortium of groups that's looking to move data science workflows to the GPU itself. It enables multi-node, multi-GPU distribution of deep learning and machine learning processing. It works really well on tabular, I think of it as like phone book type data. But what you can get by integrating these types of things, like in particular, we worked really hard on an XGBoost implementation, is a massive reduction in the cost of the compute you would need to run an algorithm of that size, the power and the physical space to host that equipment. And then the last thing I wanted to highlight, all of these things combined have really led to us performing really well in the ML4EO benchmarks. And this kind of got me thinking, you guys are talking about benchmarks and things like that. We contributed to the consortium of ML4EO. So there might be some groundwork inside the ML4EO project to kind of come up with the geospatial ML4EO for you all to hit your standards and benchmarks. But anyway, so that's how teamwork makes the dream work.
Hi there. I'm just recovering from a flu. I'm harmless. But if I cough, I apologize in advance for that. So my background is in workflow systems, and I have a group which develops workflows for data science. It's sort of a new branding of an old technology in a way. Workflows have been around for a while, but what we've seen more and more over the last 10 years is, as we heard from our speakers this morning, ML influence in workflows. So it's not just HPC, it's not just ML or data science techniques, it's a combination of them. So I'm going to talk, and we focus a lot on applications of all sorts that combines big data with scalable computing. So this is an opportunity in that sense. In real time or in near real time, this becomes what we call dynamic data-driven applications. So influenced by data as dynamic as the application needs. It could be instant in some cases. It could be, if it's a cancer application, throughout the lifetime of the patient's progression. So these are everything from manufacturing to drug discovery. We've seen like scientific applications in May's slides. 2 of them come from SDSC actually, those little thumbnails. That was nice to see. But smart, personalized, you know, you name it, precision. This is sort of the news of data influencing that age-old area, right? There's a sensor in it, that sensor is able to communicate something, or there's a measurement of some data, and we are using it to make that better. So that's what that means, right? So for geospatial big data, you know, I've been in field trips. I've seen some faces in some of those field trips. George was in one of them, I think, in Yosemite. So there are boutique data sets that are blood, sweat, and tears months. And I had a whole appreciation of those data sets after those field trips. But now we are also talking about huge data sets, remotely sensed. And every geoscience lab has an opportunity to combine what they have with what they are measuring. But these are, of course, the promises. They're highly valuable opportunities there when you do this. But there's all kinds of big data issues with it that geoscience labs itself can solve, right, themselves. So what we are discussing here relates to it: size, complexity, quality, speed. And once you get over these, if we can help the community to get over these, and I think what we are discussing here is highly related to that too for remotely sensed data, remote sensing data, the value will be there. So what we are trying to constantly do is take data, take computing, and push the data to this high value zone in all kinds of application areas, not just in earth sciences. I picked the imaging for medical, biomedical, excuse me, imaging here. If you can do something in the middle, you can annotate things and you can expand the communities that uses, you can expand collaborations with it, you can put more context into the data or commoditize the visualization of that data and findability of that data. There's a lot that can be done. So then it's amplifying the data related to X and using it for benefit. So our application that I'm going to talk about today is the problem of fire modeling. Can we collect data related to fire modeling and enable the science community to use it in a dynamic data-driven fashion? That's what we started with as a goal. And turns out fire modeling depends on weather forecast, real-time weather, fire perimeters, and landscape data. So landscape data itself is, in some of the talks we heard and we will hear, the land cover data. So here the goal was then, can we create an intelligent and integrated platform? Not just integrated, intelligent is also, because we need location-specific information in the right context. If I can use 5-kilometer data and it serves my purpose, I can use it. But sometimes I need to go to 1-kilometer resolution. How do I know that it needs to be a part of finding the data and using it for that purpose? So Wi-Fire.ucsd.edu was funded by NSF. And it was initially built as a cyber infrastructure. That's when we started working and for cyber infrastructure for fire science community. Give them the best data, best computing infrastructure, best workflow so fire science can advance. But we noticed when we started pulling our examples together, we were already doing pretty good for operational purpose that wasn't existing before, just bringing the data together. And it became operational on its own. Firemap.ucsd.edu is, excuse me, is the platform that's operational, which sort of gets mentioned a lot. But Wi-Fire is the infrastructure, and the true innovation was there. Can we combine data science and fire science to bring data together in real time for taking advantage of it as it's being produced? So the products of this infrastructure are definitely data integration and management services that has machine learning in it for curation of data, real-time data-driven fire mapping services that got to be operational, but also workflows to automate these operations so anyone can take advantage of it openly. And this led to a growing community and a lab of its own now, and we are both research and operational in the parts of that lab. But some of that research in there is really just inference to learn from remote sensing data and bring more context to data as we are working with these data sets. Of course, there's also what we do best is the dynamic scalability and workflow automation and optimization and things like that. But it's really to curate the data. How do we create the best data for fire modeling is a big part of what we do. So, oh, of course, PDF, I nicely wrote over my slides, but it could be automatic smoke detection from imagery. It could be prediction of location-specific fire weather conditions. It could be NLP for understanding what's going on in that radio. So can we get local information from firefighters' communication? But it could be also land cover information because the land fire maps are great and they're the only source right now for this type of fuel biomass information. But they are published every 2 years and they are lower resolution than what some of the fire models can take advantage of today. And over the course of a week or even a couple of days even, fuel conditions change. So we started with the idea is can we just fly a drone or get high resolution satellite imagery and update these databases? You know, they're already useful to start with, but can we make them better? And, you know, it was a purely basic science approach. It is still, you know, we are still exploring with it, but we worked with Digital Globe and Planet to get 0.5 meter resolution data sets on some parts. And we did it for some extent, so San Diego. We are tiling imagery, the workflows, and apply feature extraction and put related features together completely in an unsupervised fashion. And then we try to label those. And it's definitely challenging. You know, that would be one of the clusters you're seeing, for instance, and you would see where those clusterings happen. And it's just application of existing methods and there's a huge room for improvement in, you know, we used graduate students to label some parts of San Diego, right? There's active learning and crowdsourcing that could be used for these. But turns out once you use these land cover information and, you know, try to label them correctly, it can lead to many different uses. It's not just fire, right? As we all know, land cover information can be used in different contexts for urban development, economic development, and conservation types of scenarios. And the same techniques, there's using the generated data for applications, and there's using the workflows to transfer them into different application areas. So a map of slums in Mumbai is something we've done, for instance, just by unsupervised imagery. We were able to identify where slums in Mumbai is, but then when you go and apply the same thing in London, you won't find it, right? It's not. We looked at growth of refugee camps. We looked at, I think my time is up. We looked at land cover specific classification in San Diego and how it informs some of the changes over time. And we also looked at finding schools in Africa together with UNICEF for sustainable development efforts there. And these are just examples. It's not, done and it could be used in production mode, but these are examples that depend on training data and better training data, being able to use what is out there as methods and combining it, what's out there with data that could be made better for these different types of scientific purposes. Thank you.
Hi, I'm Andy. I work for Facebook. I'm going to talk about how we build data products that we use for social good, and especially our high-resolution settlement layer that we're publishing. I work on the spatial computing team at Facebook, which is part of infrastructure strategy. How do I? Oh, okay. We work with a lot of partners on these. These are only a couple of those that we got logos from in time. There's tons of collaborators that we have in the data for good realm at Facebook. But today I'm going to talk about the high resolution settlement layer that is here. This one. Yeah, so this one. We also do a lot of road detection that we feed into OSM directly. And we work on disaster mapping. So most of our maps are currently used to fight the Australian wildfires, for example. For the high resolution settlement layer, for people who don't know what that is, we use Maxar's 50 centimeter resolution data, detect individual human-built structures, work with CSIN at Columbia University together to assign number of people per building, and then we publish this on a 30-meter raster. When we started on this venture in 2014, this project in terms of Silicon Valley is like a dinosaur. This is what we thought. Ingest high resolution satellite image data, train a classifier, collaborate with somebody who has census data to assign number of people and publish the results. Easy. But sounds simple, so wrong. This is only some of the problems that we ran into, right? So get high resolution satellite image data for the first time at a company is like a thing. So we have to find a data center that's close to Maxar's data center so that the latency for on the order of petabytes of data is not too high. Then munch that into something that your MapReduce infrastructure can talk to and understand. Then not kicked out by all the other teams that you're suddenly hijacking their infrastructure to compute all this stuff. Eventually, Facebook opened a new data center. We were the first ones in there, caused power instability immediately after using all the machinery. Got emails about this, printed them out, put them in as badges for ourselves. Yeah, then training data is a big problem. We made very easy headway initially by just using the plain image classification platform that Facebook has, which every image that gets uploaded to Facebook runs through. This is used mostly for things like screen readers. If you're visually impaired, you use a screen reader, there's an algorithm that reads to you what's in that image. There's two people standing in front of a lake, one is smiling, the sun is shining, there's some trees, there's some clouds in the sky and stuff like that. We used that instead of the classification layer. We just took the feature vector, trained an SVM on top of this, got very good early results, but then hit diminishing returns really, really quickly. So then we started to train our own purpose-built infrastructure that was much less computationally intensive because it didn't have to extract like 3,000 features or so. and was much faster, therefore, and much more sane in terms of computation. But still, training data is a hard thing. So at first we labeled images ourselves, which you can do, but it's like you don't want to do it necessarily if you really want to get to the meat of things. We had to find an infrastructure so that we can hire people to do this for us. And then setting up a collaboration with CSIN, which is a NASA-funded institute at Columbia University. Columbia University has one of the most conservative legal departments in the US, I would say. So getting our legal department and their legal department to work together is another thing. And then of course, you eventually want to publish the results. So you have to get company approval. You have to go through all the hoops to do this. But eventually we got there. So here are some of the things that we're now doing, and we're still doing. So we built a combination of different nets for the classification that works reasonably well. So here you see some of the outputs. So in terms of like detecting masks in which we think there is a house, and then doing some more house footprinty things. And this is some of the outputs that we generate with this. So by now, India has something north of 1.2 million square miles. We can classify it now in less than 12 hours, if you're not counting the labeling. So if you use any Maxar data, you know the data comes usually in production blocks. India has multiple of those. We do things now by production block. Per production block, there's on the order of 10,000 images, 10,000 samples that we pull, and then have a team of labelers label them so that we can run our verification algorithms and procedures on this, so that we can dial in the threshold of housiness above which we think something is a house or not. That takes longer than the 12 hours that we use to just run the classifier, basically. One of the big challenges that we hit early on was that the Earth is like, the covered land area is only about 1% on average. So when you randomly sample from available land area, you have a high imbalance in terms of training data. You have 99% negative samples, 1% positive samples. We had to find good ways of balancing this for training purposes, also for evaluation purposes. Because if you measure your accuracy with 99% negative samples, you can represent the negative area really, really well, but you have problems in dense urban areas, right? So dense urban areas became a challenge. Initially, the first 23 countries that we bought data from Maxar, then DigitalGo, we were mostly focused on rural areas, but now slowly the focus is shifting to dense urban areas. So we want to become better there. So we had to change out all of these procedures to better represent dense urban areas, for example. This is I don't know if this will play. This is some comparison. So Mark showed this at a fireside chat at Mobile World Congress, I believe like 2 or 3 years ago. This was the state we were at then. So this is GPW4, which some may be familiar with. It grids census data at 1 kilometer, but it's not true 1 kilometer resolution. This is what we're doing. So now this is some area in Kenya. And you can really see and appreciate the difference between like the state of the art that the GPW used to represent and what we're doing. Yeah, so far we've published 190 countries, and we're increasingly adding demographic data to this, so age breakdowns and gender breakdowns. The next steps for HRSL will be to incorporate building volume, at least at a course level. So we're trying to get to a data set of building volume. And then we're trying to get to sub-census boundary population growth modeling, which is currently not the case. Currently, we uniformly distribute people in the census area over the structures that we identified, but now we want to distinguish by type of building, distinguish by size of building, and also want to be able to track the settlement growth over time, going backwards in time, saying, hey, this settlement has grown by X, that other settlement has grown by Y, and we want to distinguish those. That's it. You can find more information on our disaster mapping efforts, the road mapping and pop density and these things, and I'm around for the 2 days.
Hey, so I'm Stephen Brumby. I'm at National Geographic Society, where I lead geographic visualization. Before that, I was the technical founder of a VC-backed startup called Descartes Labs, which does a lot of global scale agriculturals and other types of analysis. And before that, I was at Los Alamos National Lab for a long time doing this type of stuff for Gov. So what are we doing at National Geographic Society? And thanks, Hamid, for the opportunity to be here today. Absolutely agree with everything that's being said here this morning. The big bottleneck to really doing machine learning at scale is the lack of training data. I've struggled with that my whole life, my whole career, and I got sick of it. So we're trying to do something about it. National Geographic Society in particular, we are mostly looking at the world's most remote places. So, you know, if it's the place that gets the least coverage from Maxar/Digital Globe, you know, aka Digital Globe and Airbus and everybody else that actually has good satellites, we're the last ones to ever get coverage of the places we care about. So for us, we have to ask, what's the state of the art for global land use land cover, which is ESA, and NASA also has 500-meter stuff. NASA goes up to 2018. ESA has 300 meters versus 500 meters. So there's trade-offs between the two, but they're not really good enough for what we want to do. Now, on the other hand, USGS, and I think I saw Pete Doucette here somewhere, as the NLCD product, which is going to turn into the NLC map product, 30 meters US every couple of years, really nice product, only available for CONUS. Brazil's got map biomass. The Canadians and the South Africans have got some similar stuff. Again, regional scale, nothing global. On the other hand, there's Sentinel-2 everywhere. Why haven't we made a global land use land cover map yet? We know there's different teams working on it. We're working on this very, very actively. So what we've done is we've put together a consortium. It's ourselves, World Resources Institute, and I see Brookie's here from World Resources Institute, and Google. And in fact, my colleague Chris Brown will be talking tomorrow on some stuff. And which I'll give a small glimpse of. And we're in this partnership. We want to be able to get to a Sentinel-2 10 meter per pixel land use land cover time series for the world. And to get there, you need training data. How much training data do you need? That's a good question. Nobody knows for sure. We do know that, for example, there's some academic data sets. Matt Hansen, who makes Global Forest Watch. Nobody knows how much ground truth data set Matt Hansen actually has. As far as I'm aware, he's not released it openly. Good for him. He's very successful academically because of that data set. We don't know exactly how much data he has. It's the best one. Estimates on the street from unacknowledged sources says that it's about 1 million pixels per category. Let's say you want to do 15 category global land use land cover. So maybe you need 15 million training pixels. If you consider all the pairs, then suddenly you need 200 million training pixels. We don't know. One of the key things with ImageNet and with SpaceNet is that people are and before that, MNest, is that you push the boundary of, by basically going up in orders of magnitude, you try and find where hopefully you get a phase transition in the performance of machine learning. We don't know where that phase transition is going to happen yet, so you have to go big. So what we're doing to feed this machine learning system that everybody knows we want to try and build is to have a lot of data. So similar to what Hamed mentioned, we're also gone and done a sample of, in this case, we have tens of thousands of tiles. Each tile is 510 by 510 pixels. I'm enough of a computer scientist that 510 versus 512 really bothers me, but it is actually 510 pixels for some reason. 510 by 510 pixel tiles from all over the world. These are designed to sample from all the world's major biomes, which is the sort of We don't, in Nat Geo, we care less about countries than we care about biomes and ecosystems. So sampling across all the biomes. We have a taxonomy that was created by our colleagues at World Resources Institute, who did a landscape survey of all the different taxonomies that are out there. As you would expect, they're about 90% consistent across all the different ones. So, but this is a very important question, and very much agree with Hamid's questions about interoperability. You need to think about how to do this. In terms of markup, I've personally built markup systems like this several times over my career. Every time I build it, it ends up being proprietary. There's a real problem with having openly available ones. The first team to make a really good openly available tool, I applaud you. We're actually using a commercial system done by guys called Labelbox, folks called Labelbox, who also built this system multiple times for different people and have now gone and spun themselves out in their own VC-backed thing to do this. And this, the key thing about this tool, that why we chose it, is that it allows dense markup, polygon-based dense markup. Because you have, for example, Gong et al. At Tsinghua, who have a 300,000 pixel training set. You have BigEarthNet from the European Union with 500,000 individual pixels. I know from all my career that dense markup, especially for the spatiotemporal spectral algorithms you can learn with deep learning, that's what you really want. So we need more tools that do polygonal markup. This one does, so we chose it. And so we're producing markup that looks like this. Now, Hamid mentioned that with the Radiant Earth training data set, which is an independent effort from ours, one of the design criteria is to have no spaces between pixels. Here you can see there are some spaces. This is an interesting difference. In our case, we wanted to get through a lot of tiles, so we instructed our folks to do as much as you can, but don't try and get every single pixel. Plus, quite frankly, the humans can't decide on some of those edge cases. And so, we're doing this, and we're going to evaluate carefully, and we'll be very interested to compare to the Radiant Earth data set to see what the difference is. Another thing we did was, how do you cross-validate? So one approach to cross-validation is to have lots of people at the same level who basically all just look at each other's work and try and figure that out. I actually did that years and years ago with a bunch of graduate students at UC Santa Cruz, cross-referencing each other on counting craters on Mars. And the funny thing was, the students, we didn't tell them that they were cross-checking each other's work. And you think counting circles on a gray image would be fairly straightforward. There was 50% variance when we looked across all the undergraduate students in a paper that's at LPSI. So what we did here was we had human photo interpretation experts mark up about 10% of the data. And then we occasionally give these same images that the human experts have marked up to this semi-professional dedicated workforce that's offered by Labelbox. And we've got some results that we showed at AGU in December, and I'm happy to go into the details for this, anybody who cares. Here's our little tease of the initial results that we're getting, because one of the key things about training data sets is, how do you know it's any good? The only way you know it's any good is if you actually try and use it for something. So in addition to making the data set, one of the key things about this consortium is that we're actually also going to release the model and the map that we produce. All of those three things as open science data products. So thousands and thousands of tiles, which at 510 pixels by 510 pixels and thousands of tiles and 80% fill factor, we're talking about a 1 billion pixel human labeled data set compared to the BigEarthNet 500,000 pixel or the 300,000 pixels of Gong et al. So over 1 billion human labeled pixels, actually it's several billion if you do the math. We want to release that, but we also want to show what you can do with it. So here's a very, and this is probably stealing some of Chris's thunder for maybe, but this is a result that Chris showed last December again at AGU. Here's some Brazilian Cerrado, so it's not the usual forest stuff, but it's like light forest-ish. Here's the ESA map from 2015, so it's 4 years delayed, latest available, and at 100 meters, which is only available for 2015, it's still, you can see the crudity of the 100 meter data. Map Biomass as a 2015, they actually also have a 2018 result at 30 meters, which is clearly a lot better than the ESA data, but is out of date. And here's the key thing, at 10 meters, with the taxonomy we showed before, these are the categories that are in the scene, we're starting to resolve settlements. They're not visible in the other land use land cover maps. So as we scale this up to the rest of the globe, and we are expecting to complete the technical work on this before the IUCN World Conservation Congress in June, and to release it on that timescale, we are hoping to release the data set and the model and the software to run the model as open science data products. And I'm probably out of time. I've got 1 minute left. Good. I'll just say the 3 things that we want to do with this once we have this, and this is all in software, so we can run it over and over again. And because the Sentinel-2 data comes down in such volume, there's no reason that you can't do this more than annually, right? Quite frankly, except modulo clouds. But there's ways around that, thanks to synthetic aperture radar and other stuff, potentially. Also potentially by folding in Landsat as well. If your training data is at 10 meters, you can gracefully degrade it and try and train at 30 meters as well, and then go back through the full Landsat time series. But at the moment, what are we going to do? We're going to look at land conversion processes. Global Forest Watch does deforestation and forest aggregation up to 2012. We want to do it for all the different land cover changes. We want to be able to generate things like deforestation alerts, but do it tied to biodiversity conservation areas of interest. So for example, here's the range extent for a particular subspecies of giraffe, and we're looking at habitat impact for that particular species. Imagine monitoring every species in the world and automatically reporting on the status of its habitat, continually updated through time and with a full time series. And finally, when you have multiple years of this thing, you can start to look at large scale unintended consequences. So when the US changes ethanol rules, which happened during the George W. Bush administration in back in the early 2000s, that with a few years delay triggered massive change in land cover in South America to produce soybeans because the farmers switched to corn in the US. What was the long-term real impact? When the European Union puts in biodiesel standards in Europe, thinking that it's green, what does that do to palm oil production in Southeast Asia? There's large-scale, long-range connections between land cover conversion processes which are not being properly illuminated at the moment. And by doing this work, we hope to shine a bright light on all this. Thank you very much.
Good morning, everyone. My name is Nana Yi. I'm currently a machine learning engineer. As I already introduced, I come from academically trained spatial modeling on nature resource management. And here I've been building a lot of ML applications from searching for school from high resolution satellite imagery with UNICEF. I heard that UC San Diego has done that with us in the first phase. And it's still ongoing, and we moved to Colombia. And I also run deep learning object detection on street view imagery to searching for vulnerable housing in developing country. We have done South America, Central America, and now moving to Asia with World Bank. And today, this is a big title, but we haven't solved it, just let you know. Just in 2019 was an exciting ML application year at DevC. And here is we built a deep learning hurricane wind estimation with NASA impact team. Rahul is here, and he knows much more than me if you want to outreach. And this is image classification that inspire us for multiple implication. For example, school search from high resolution satellite imagery is image classification. And another project we've been doing is with European Space Agency that, in this deep learning community, a lot of tool has been developed to be easier to implement it in a lot of applications, not only EO data. And this is we are doing an experiment with a project called Query Planet and using Fast AI. Fast AI is just like a train the model for you, but on the other side, it's hard to scale up the model inference. How can we run the model in a a speeded way that can output the result faster enough for any decision making on the ground. So this is Drew Bollinger at DevOMC has built a chip scale and fast AI serving, and this is a real-time prediction of land use and land cover models we built. And next one is also like, machine learning application is very user-centric. That's how we define ML application at DevC, that we start working with a partner who actually like care about user-specific application. For example, we work with Severe. Severe is a joint program between NASA and USAID that connecting space to village. And each village might have a specific use cases. For example, we build that water detection example that a farmer can use to track the water body change underground, so they can manage. They can better plan their irrigation, and also land use and land cover with fast AI was one of them, and a crop type mapping that officer on the ground who can use the crop type to map the food security, as well as like what kind of agriculture insurance schemes that they can design to sort of manage the either the nature disaster or like application on the ground. So ML would say ML is not that very straightforward, right? Like we have image classification and object detection and pixel-wise semantic segmentation. As Oak Ridge National Lab start to talking about like limited labeling and how we can use like weekly supervised machine learning on this. And fundamentally, we want to this ML framework to be flexible enough and also low cost and scalable and maintainable, that is open source, that we can have a collective contribution from the community. And I think we can learn a lot from PanGeo from this site, especially for data preparation and data storage. And like in DevC, we have Earth data infrastructure that who's building scalable, and also the pipeline that can help our any like satellite provider to scale up the image serving faster, and Earth analysis teams like sit on top of the infrastructure team. And we do have a very strong opinion of like how the ML model should be running better on the Earth infrastructure. And this is Vincent, like he's like big advocate for dynamic tiling and cloud optimized GeoTIFF, especially like like dynamic tiling, like sit on top of the cog, can allow user to interact with raw data and can process image faster, and also that they kind of like mosaic can serve spatial and temporal representative of set of cog, and you can do like pixel selection faster, and we can serve selected pixels from any cloud provider, like with very lower cost compared to current the way the image was serving. And we're also working with NASA Goddard science teams to harmonize the Sentinel-2 and Landsat imagery that in the way is comparable and treatable for any analysis. And when it's come to like, like neural nets, there's a lot of parameter to train, and it's not that straightforward, I would say. And, as a machine learning engineer, we kind of like making decision on the daily basis, like what satellite imagery are available, what applications, and what training data set and what training data set has been formatted and will be formatted, and also like, you know, like, do I go to classic machine learning methodology first, or is deep learning is more like cost effective, and how we containerize this model to share across departments with colleagues, and also like how we can containerize training model that we can run model inference faster. And this is not a simple solution, so I'm glad to be here today that join the conversation, and you know, we're so many bright minds, and this is great opportunity to learn and to kind of like make a plan for next. That's it.
Okay, hi everyone. I'm Gencer Sümbül. I'm a PhD student and research associate at Remote Sensing Image Analysis Group. Our group is led by Professor Begüm Demir at Remote Sensing Image Analysis Group of Technical University of Berlin, Germany. Today, I will introduce the BigEarthNet, and then first I will explain how we created it, and then what type of problems we observed and how we solve them. But not all of them, just some of them I will explain. BigEarthNet is a new large-scale Sentinel-2 benchmark archive, including almost 600 Sentinel-2 image patches. And to construct the BigEarthNet, we selected 125 tiles, Sentinel-2 tiles, between June 2017 and May 2018. And these tiles covers 10 countries of Europe. You can see the countries there. And all the tiles were atmospherically corrected. And then we divide all the tiles into image patches. And each patch has the size of 120 by 120 in 10-meter resolution. But we have also 20-meter and 60-meter resolution bands. And then we associated each patch with one or more land cover class labels, namely multi-labels provided from the Korean database of the year 2018. And CLC 2018 is provided from the European Environment Agency. And here you can see the distribution of the classes and their names. And there are 43 classes in total, and the number of labels associated with each patch varies between 1 and 12. And you can see some example here. And it's worth noting that we include images from different seasons, and you can see the numbers here. And after creating the archive, we also visually identified the patches that includes cloud shadow, and seasonal snow. And we are not suggesting to use them for deep learning applications, but if you are dealing with the tech-based image classification, multi-model classification, you can use them. Or for cloud or snow detection, you can also use. But if you neglect them, 520,000, almost 520,000 number of patches remain. And here I will give 2 examples of use cases for the BigEarthNet. First one is content-based image retrieval. Once you have an image which is associated with a specific semantic content, and image retrieval aims to find the similar images from the Earth. So, for instance, here we have a burned forest, and we are trying to find the similar images from the Earth, so similar burned forest areas. And the second example can be image scene classification. Since we have multi-labels, and you can use the BigEarthNet to automatically assign the labels to image scenes. So you can also use it for image scene classification. But in addition, you can also use the BigEarthNet for imbalanced data learning, transfer learning, super resolution, VGI exploitation, scalable image classification, active learning, and so on. Since we introduced the BigEarthNet mainly for deep learning applications, we also published the pre-trained deep learning models on the BigEarthNet for the use of community. And just one thing I want to emphasize here, that we also compare our pre-trained models with the pre-trained models trained on ImageNet. And you can realize from the results is that if you use the BigEarthNet, if you train any deep learning model from scratch, you can really gain a huge performance. Here you can see the results for just one deep learning model, but we compare it for almost all the state-of-the-art deep learning models, and we observe the same behavior for all of them. So we are suggesting not to use pre-trained models trained on ImageNet. You can directly use the models trained on BigEarthNet. But after obtaining the results, we observed that some CLC classes are challenging to be described by considering only the single-day Sentinel-2 images. Here, for instance, maybe I can show you. Yeah, here for this patch, we have a rice fields class, and the characteristics of this class are changing too much from season to season. So it is not easy to describe, not easy to detect these classes for scenes. So in collaboration with a group from Lisbon team, we started to work on new class nomenclature, new classes, class labels. And then very recently, we also published the BigEarthNet 19 with a new class labels. This is achieved by interpreting and arranging the original CLC classes based on the properties of Sentinel-2 images. Now it is publicly available. It's very recently from us. I think yesterday we did it. So we also published the pre-trained models on BigEarthNet 19, so you can also use them. And if you check the details, our preprint, archive preprint is available. You can also check. And so in terms of the impact of the BigEarthNet, we actually published it 11 months ago, and until now, almost 9,000 users has entered our websites. And meantime, many papers are published with BigEarthNet. And also BigEarthNet is also included in TensorFlow for the direct use of deep learning application. Here you can see the distribution of the countries that uses the BigEarthNet. And I can say that actually BigEarthNet has attracted the attention of the community. And what is next? Actually, we plan to enrich BigEarthNet by extending the BigEarthNet to whole Europe, not just the 10 countries, the whole Europe. And also we are planning to include the Sentinel-1 patches and also auxiliary data like digital elevation model. And also we are planning to include the class-wise appearance percentages for each patches so they can help deep learning applications. So we believe that BigEarthNet will make a really significant advancement for the use of deep learning applications by overcoming the current limitations of the existing archive. Here's the end of my presentation. Thank you for listening to me.
Hello. I'm going to tell you about a study we undertook at CosmiQ Works last year, looking at the question of how much data do you need for geospatial deep learning? But before we get into that, let me tell you a little bit about CosmiQ Works. Our goal is to accelerate capabilities for analyzing overhead imagery and satellite imagery in particular. And we do this in a number of ways. One way is that we undertake research projects of our own. These are at the intersection of computer vision and geospatial analysis, and often focused on the area of foundational mapping, which in turn is very useful for things like disaster response. We also, with our industry partners, run SpaceNet, which open sources or releases open source high quality labeled data sets of overhead imagery. And you've heard about that from Subit already. So with these data sets, there are data science challenges. The winners get prize money and everyone else gets the winning algorithms, which we open source with SpaceNet. And really open source is central to a lot of what we do as well. So at CosmiQ, we open source a lot of the code that we write, including Solaris, which is our pipeline for machine learning of geospatial analysis. We also undertake market analyses to better understand the technological and economic context in which all of this is happening. But onto the topic of this talk, which is understanding how model performance for deep learning models on geospatial imagery varies with the quantity of training data. And to be specific, we'll look at models to extract building footprints from optical satellite imagery. So in asking the question of what that dependence looks like, it will also raise two follow-up questions. The first being, does the answer depend on the model architecture we're using? And the second being, does the answer depend on the geographic location we're looking at? And the answer to both of those will end up being mostly no, but with some caveats. So here you see some pictures of kind of what we're doing. Extract pixel segmentation from the imagery, which gets better when you have more training data to work with. From the pixels, you extract building footprint vectors, which are what you can then evaluate compared to ground truth labels. So we did a pipeline with this, like this, looking at satellite imagery of Atlanta, Georgia, from a bunch of different viewing angles over a wide range of off-nadir angles. And I'll jump right to the result. It looks like this. So the x-axis is the amount of training data. The y-axis is how well the model did, according to a metric which we can discuss in more detail later. And the different colors of lines just correspond to different ranges of viewing angle within the testing data. Now, what you can see here is that when there is very little training data, even small increases in training data cause big jumps in performance. But that rate cannot be sustained. Once you get to higher and higher amounts of training data, you get into this regime of rapidly diminishing returns. And the fact that the data has this shape brings about an interesting result. If you look at the points on the very right-hand side of that plot, those correspond to training on 27 different views of 160 square kilometers of ground. That's a lot of data, and it gives you a performance that's very good. But I can get 2/3 of that performance using 3% of that training data because of this shape. In looking at this, we thought about methods to describe what's going on. This is the same plot, just with a logarithmic x-axis. You see we have error bars there. Those were calculated for some data points by repeating the training and interpolated for others. The dotted lines are empirical fits to the curves. For this class of problems, this very simple mathematical function that you see there ended up working surprisingly well. So, first follow-up question, how does it affect things with using a different model? So here the light curves are what we just saw before. The dark curves are repeating the exercise but with a different model architecture. And what you see is the same basic shape, but the performance is different. And something interesting happens here. If you have an intermediate amount of training data, this new model is far better. If you're over on the right-hand side, the new model is only barely better. And extrapolation indicates that with just a little more data, the old model would actually be the one that wins. The reason why this matters is if you ask me which model has the best performance for this task, I can't answer that unless you also specify how much training data is being used. So this calls attention to the fact that there are cases where model architectures cannot be ranked in an absolute sense without knowing more information, and in particular, how much training data. Another question we looked at was how things vary with different geographic areas. So here you see plots like the one before of performance versus amount of training data for 4 different world cities. All the data that you're seeing here today is being drawn from SpaceNet. That Atlanta data was the SpaceNet 4 data set. This is now the SpaceNet 2 data set. And what you see here is that across these cities, that same overall trend takes place. Rapid rises when training data is scarce, followed by diminishing returns once it is plentiful, although the overall performance does vary by city. And something interesting can be looked at here, and that is what happens when you combine data from multiple places. So for each city, there are really two lines up there you can see, the lower darker line and the higher lighter line. The lower darker line for each city is the performance of a model trained just on data from that city, with the amount of data being as shown on the x-axis. The higher lighter line is the performance of a model trained on data from that city and the amount shown on the x-axis, plus an equal amount of data from all three of the other cities. So in that case, we're helping the model out by giving it 4 times more data, but we're also asking it to do a harder job, to be a general purpose model across these cities from all over the world, instead of just applying to one. And that second case, in terms of performance, wins every time. There's a lot more that could be talked about just with this plot, like why those lines are spread out and why they have different behavior as you go to load data. And maybe we'll get into that at another time. But for now, just to hit the key points, models trained with a small fraction of the training data may perform surprisingly well. And making plots like these are how you can understand the benefits of that versus the benefits of going and acquiring more data than you already have, things like that. Methods like using error bars and empirical fits help you understand what's going on, help you dig into the differences in your underlying source data. And finally, if you're looking at something like this, where you have maybe multiple cities, and you have the choice between training a separate model for every single one, or piling together all the data you can get your hands on to make a general purpose model, in a case like this, the general purpose model is the way to go. If you'd like to learn more, we have a blog, we have a GitHub, we have a podcast, or you can just ask me. Thank you.